National Electrical Code Article 406.4 DUN requires ground fault circuit interrupters, also known as GFCIs, for receptacles in hazardous classified locations and in other locations where water is likely to be present. Classified locations are defined in Article 500 of the National Electrical Code and typically involve the presence of flammable or explosive materials. Laboratories do not typically meet the criteria for classified locations unless flammable materials are specifically used or stored. The National Electrical Code defines locations where water is likely to be present as firstly, areas where water is normally used or handled, such as bathrooms, kitchens, and laundry rooms. Secondly, areas where water or other liquids may accumulate, such as basements and crawl spaces. Thirdly, areas where water may be sprayed or splashed, such as near showers, sinks, and dishwashers. Laboratories often have sinks and receptacle outlets close to the sinks, where water may be present. While laboratories may not typically meet the criteria for hazardous classified locations, they may be considered locations where water is likely to be present. Based on the National Electrical Code, the general requirement for GFCIs in locations where water is likely to be present would apply to receptacles in a laboratory near sinks. Therefore, GFCI receptacles would be required in such applications for personnel protection. Let's delve deeper into the requirements for ground fault circuit interrupter protection, or GFCI, as it relates to electrical safety and compliance with the National Electrical Code. The primary purpose of GFCI protection is to protect people from electrical shock. A GFCI is a fast-acting circuit breaker that senses small imbalances in the circuit caused by current leakage to ground. If a person comes into contact with a live electrical component and provides a path to ground, the GFCI will trip, cutting off the power almost instantaneously. This prevents serious injury or death. The National Electrical Code, which is a widely adopted standard for safe electrical installation, mandates GFCI protection in various locations where the risk of electrical shock is heightened. Article 406.4 DUN of the National Electrical Code specifically addresses GFCI protection for receptacles. The key takeaway from this article is that GFCI protection is required for receptacles in locations where water is likely to be present. This includes, but is not limited to, bathrooms, kitchens, laundry areas, and locations near sinks. The reason for this requirement is that water greatly increases the risk of electrical shock. Water is a good conductor of electricity, and when it comes into contact with electrical components, it can create a path for current to flow through a person's body to ground. This can result in severe electrical shock, burns, or even death. In a laboratory setting, there are often multiple sinks and electrical receptacles in close proximity. This presents a significant risk of electrical shock, as water can easily splash onto the receptacles or electrical cords. Therefore, the National Electrical Code requires GFCI protection for receptacles located near sinks in laboratories. It is important to note that the requirement for GFCI protection applies to all receptacles within a certain distance of a sink, regardless of whether the receptacle is actually being used. This is because the risk of electrical shock exists whenever there is a possibility of water coming into contact with electrical components. The specific distance requirements may vary depending on local codes and interpretations, but generally, any receptacle within 6 feet of a sink should be GFCI protected. In addition to receptacles near sinks, GFCI protection may also be required in other areas of a laboratory where water is likely to be present. This could include areas where equipment is washed, areas where liquids are stored, or areas where spills are likely to occur. The determination of whether GFCI protection is required in these areas should be made on a case-by-case basis, taking into account the specific hazards present in the laboratory. It is also important to understand the difference between a GFCI receptacle and a standard circuit breaker. A standard circuit breaker protects against overloads and short circuits. It will trip when the current in a circuit exceeds the rated capacity of the breaker. However, a standard circuit breaker will not protect against ground faults. A ground fault is a condition where current leaks to ground, often through a person's body. A GFCI receptacle is designed to detect ground faults and trip the circuit, even if the current is relatively low. This makes it much more effective at preventing electrical shock than a standard circuit breaker. There are two main types of GFCI protection: firstly, GFCI receptacles, and secondly, GFCI circuit breakers. A GFCI receptacle is a standard electrical receptacle with built-in GFCI protection. It can be installed in place of a standard receptacle and will provide GFCI protection for any devices plugged into it. A GFCI circuit breaker is a circuit breaker with built-in GFCI protection. It can be installed in a panel board and will provide GFCI protection for the entire circuit. When installing GFCI receptacles or circuit breakers, it is important to follow the manufacturer's instructions carefully. The devices should be properly grounded and tested to ensure that they are functioning correctly. It is also important to periodically test GFCI receptacles and circuit breakers to ensure that they are still providing protection. This can be done by pressing the test button on the device. If the device trips, it is working properly. If it does not trip, it should be replaced. In addition to the requirements of the National Electrical Code, there may be other regulations or standards that apply to electrical safety in laboratories. For example, the Occupational Safety and Health Administration, known as OSHA, has regulations that address electrical safety in the workplace. It is important to be familiar with all applicable regulations and standards to ensure that the laboratory is a safe environment for workers. Another important aspect of electrical safety in laboratories is proper grounding. Grounding is the process of connecting electrical equipment to the earth, which provides a low resistance path for current to flow in the event of a fault. Proper grounding helps to prevent electrical shock and equipment damage. The National Electrical Code specifies the requirements for grounding electrical systems. It is important to ensure that all electrical equipment in the laboratory is properly grounded in accordance with the National Electrical Code requirements. This includes equipment such as receptacles, lighting fixtures, and machinery. In addition to grounding, it is also important to use proper wiring methods in laboratories. The National Electrical Code specifies the types of wiring that are permitted in different locations. In general, wiring in laboratories should be installed in conduit or other approved traceways to protect it from damage. Wiring should also be properly sized for the load that it will be carrying. Overloaded circuits can overheat and cause fires. Regular inspections are crucial to maintaining electrical safety in laboratories. These inspections should be performed by qualified personnel who are familiar with the National Electrical Code and other applicable standards. The inspections should cover all aspects of the electrical system, including receptacles, wiring, grounding, and overcurrent protection. Any deficiencies that are identified during the inspection should be corrected promptly. Training is another essential element of electrical safety in laboratories. All personnel who work with electrical equipment should be trained on the hazards of electricity and the proper procedures for working safely. This training should include information on GFCI protection, grounding, wiring methods, and lockout-tagout procedures. Lockout-tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. In summary, GFCI protection is required for receptacles near sinks in laboratories to protect people from electrical shock. The National Electrical Code mandates GFCI protection in locations where water is likely to be present, and laboratories with sinks fall under this requirement. Proper grounding, wiring methods, inspections, and training are also essential to maintaining electrical safety in laboratories. By following these guidelines, laboratories can create a safe environment for workers and prevent electrical accidents. Let's talk a little more about the technical aspects of GFCIs. GFCIs work by monitoring the current flowing through the hot and neutral wires of a circuit. In a normal circuit, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. However, if there is a ground fault, some of the current will leak to ground, creating an imbalance between the hot and neutral wires. A GFCI is designed to detect this imbalance and trip the circuit very quickly, typically within a fraction of a second. The tripping threshold for a GFCI is typically around 5 mA. This means that a GFCI will trip if it detects a current imbalance of 5 milliamperes or more. This is a very small amount of current, but it is enough to cause a dangerous electrical shock. GFCIs are designed to protect people from electrical shock, but they will not protect equipment from damage. If there is a ground fault, the GFCI will trip, cutting off the power to the circuit. This can prevent damage to the equipment, but it is not the primary purpose of the GFCI. There are several different types of GFCIs available. The most common type is the receptacle type GFCI, which is designed to be installed in place of a standard electrical receptacle. There are also circuit breaker type GFCIs, which are designed to be installed in an electrical panel. In addition to GFCIs, there are also arc fault circuit interrupters, also known as ASIs. ASIs are designed to protect against fires caused by arcing faults. An arcing fault is a type of electrical fault that can occur when there is a loose connection or damaged insulation in a circuit. The arc can generate a lot of heat, which can ignite nearby combustible materials and cause a fire. ASIs are designed to detect arcing faults and trip the circuit, preventing a fire from starting. The National Electrical Code requires ASIs in many areas of the home, including bedrooms, living rooms, and dining rooms. While ASIs are not specifically required in laboratories, they may be a good idea to consider, especially in areas where flammable materials are stored. Let's explore some additional considerations for electrical safety in laboratories. One important consideration is the use of extension cords. Extension cords should only be used on a temporary basis. They should not be used as a substitute for permanent wiring. If you need to use an extension cord, make sure that it is properly sized for the load that it will be carrying. Also, make sure that the extension cord is in good condition and that it is not damaged. Another important consideration is the use of surge protectors. Surge protectors are designed to protect electronic equipment from voltage spikes. Voltage spikes can damage or destroy sensitive electronic components. Surge protectors are a good idea to use in laboratories, especially for computers, oscilloscopes, and other expensive equipment. When selecting a surge protector, make sure that it is rated for the voltage and current that it will be protecting. Also, make sure that the surge protector has a high surge current capacity. Another important consideration is the labeling of electrical panels. Electrical panels should be clearly labeled to indicate the circuits that they control. This will make it easier to identify and de-energize circuits when necessary. The label should be legible and up to date. In addition to the technical aspects of electrical safety, it is also important to consider the human factors. People make mistakes, and even the best electrical safety systems can be defeated by human error. Therefore, it is important to create a culture of safety in the laboratory. This means that everyone should be aware of the hazards of electricity and the proper procedures for working safely. It also means that everyone should be encouraged to report any electrical hazards that they see. Regular safety meetings can be a good way to reinforce electrical safety practices. These meetings can be used to discuss recent incidents, review safety procedures, and provide refresher training. Safety posters can also be used to remind people of the hazards of electricity and the proper safety procedures. One of the most important things you can do to improve electrical safety in your laboratory is to conduct a thorough risk assessment. This involves identifying all of the potential electrical hazards in the laboratory and assessing the likelihood and severity of each hazard. Once you have identified the hazards, you can develop a plan to mitigate them. This plan should include measures such as installing GFCI protection, improving grounding, using proper wiring methods, and providing training. The risk assessment should be reviewed and updated on a regular basis to ensure that it remains current. Electrical safety is an ongoing process. It requires constant vigilance and a commitment to safety from everyone in the laboratory. By following the guidelines outlined in this discussion and by creating a culture of safety, you can significantly reduce the risk of electrical accidents in your laboratory. Remember that electrical safety is everyone's responsibility. If you see something that doesn't look right, report it. It could save a life. Now let's consider some specific scenarios that might arise in a laboratory setting and how GFCI protection would apply. Imagine a researcher is working with an electrophoresis apparatus near a sink. If a spill occurs and water splashes onto the apparatus or a nearby receptacle, the risk of electrical shock is significantly increased. In this case, the GFCI protection would trip, cutting off the power and preventing a potentially dangerous situation. Another scenario might involve a student using a hot plate to heat a solution. If the hot plate is faulty or if the student accidentally spills liquid onto it, the GFCI protection would again trip, preventing a possible electrical shock or fire. In both of these scenarios, the GFCI protection provides a critical layer of safety, minimizing the risk of injury or equipment damage. It's also worth noting that GFCI protection is not a substitute for other safety precautions. It's still important to follow all established safety protocols when working with electrical equipment in a laboratory. This includes things like wearing appropriate personal protective equipment, such as gloves and eye protection, and ensuring that all equipment is properly maintained and inspected. In addition to GFCI protection, it's also important to have a clear understanding of the laboratory's emergency procedures. This includes knowing where the emergency shut-off switches are located and how to use them. It also includes knowing how to respond to an electrical emergency, such as a fire or an electrical shock. Regular drills and training sessions can help to ensure that everyone in the laboratory is prepared to respond effectively in the event of an emergency. Furthermore, it's crucial to maintain accurate records of all electrical work that is performed in the laboratory. This includes records of any inspections, repairs, or modifications that are made to the electrical system. These records can be helpful in identifying potential problems and preventing future accidents. Another important aspect of electrical safety in laboratories is the proper use and storage of flammable materials. Flammable materials should be stored in approved containers and in designated areas. They should never be stored near electrical equipment or heat sources. It's also important to have a fire extinguisher readily available in case of a fire. In some cases, it may be necessary to install explosion-proof electrical equipment in areas where flammable materials are used or stored. Explosion-proof equipment is designed to contain any sparks or explosions that may occur inside the equipment, preventing them from igniting flammable materials in the surrounding area. The requirements for explosion-proof equipment are outlined in Article 500 of the National Electrical Code. In addition to the National Electrical Code, there may be other regulations and standards that apply to electrical safety in laboratories. For example, the American National Standards Institute, also known as ANSI, has developed a number of standards related to electrical safety. These standards provide guidance on topics such as grounding, wiring methods, and equipment selection. It's important to be familiar with all applicable regulations and standards to ensure that the laboratory is in compliance. Finally, it's worth emphasizing the importance of communication in maintaining a safe electrical environment in the laboratory. Everyone in the laboratory should feel comfortable reporting any electrical hazards or concerns that they have. Open communication can help to identify and address potential problems before they lead to accidents. In conclusion, GFCI protection is a critical safety measure in laboratories, particularly in areas where water is present. However, it's just one element of a comprehensive electrical safety program. By following all applicable regulations and standards, implementing appropriate safety procedures, and fostering a culture of safety, laboratories can minimize the risk of electrical accidents and create a safe environment for everyone. The electrical safety requires diligence and is an ongoing effort. This includes not only the right technology, but also the correct safety procedures, training, and an encompassing safety-oriented mindset.